start the YouTube and then I'll introduce you. So welcome everyone to today's seminar. Today is a pleasure to introduce Angela Bragaglia, who obtained her PhD at the Bologna University in 1990. And she also spent a year in Arizona in the United States. She has actively participated in the FLAMES project on globular clusters to study multiple populations. And also she leads the BOCCI project on open clusters. Today she's going to be talking to us about the WEAVE survey and the FOREMOST survey, one in the north and one in the south, and large spectroscopic surveys. So thank you for accepting our invitation. The floor is yours.
Thank you very much, and thank you. Hello, everyone. And first of all, I thank the organizer for having me here today, and I wish to talk about stellar clusters and spectroscopy. So, star clusters come in very different types, from very young to very old, almost as old as the universe. They may have a small mass, like the open cluster in our galaxy, but they can be as massive as the smaller galaxies that we are. Stellar clusters are ubiquitous. We find them very close to us in the whole Milky Way, in galaxies close by, and in very far galaxies. Star clusters trace the stars and galaxy formation and evolution, and they are the best tools to test the theoretical models. So the importance of stellar clusters for astrophysics is clear. My talk today is divided in 3 parts, and first I will concentrate on globular clusters, and in particular on their multiple population and how high-resolution spectroscopy is essential to study globular clusters. Then I will move to open clusters and to what we can learn on open clusters, combining large surveys but also small projects, especially if we can use a very powerful instruments such as JARPS at the Telescopio Nazionale Galileo. And then, finally, I will touch on what we can expect to find on stellar clusters in the future large spectroscopic surveys. So, let's start with that. Usually, one thinks of a stellar cluster as an object composed of stars born at the same time and with the same chemical composition. So that means that we are dealing with a simple stellar population as opposed to the composite populations that we find in galaxies. And this is possibly true, but only at first approximation. So let's start with globular clusters. In the Milky Way, all globular clusters that we know are old, as it is clear from the color magnitude diagram of them. And this, I show just 2 of them obtained with the Hubble Space Telescope, where most of the points are members of the clusters with some contamination from field stars. And with the very high photometric precision obtainable with HST, if we clean the diagram from field interlopers using proper motions, the cluster sequences become very, very thin and clearly resemble isochrones. At least until we use a combination of filters where the effect of different chemical composition can be seen. So here, in this case, I cheated a little because I chose a case where We know that there is a large variation in helium abundance among the stars. However, it is clear that there is not a single main sequence, but there are different sequences at different helium level. And helium and those stars have the same general metallicity, but very different helium content. And not only helium. The 2 points shown here are for 2 stars for which we got spectra and we got abundances, and those abundances differed in light elements between the 2 stars on the helium-rich and helium-poor main sequences. And this is not an exception. Well, 2808 is a very peculiar cluster, but it's not an exception. And indeed, the multiple population story in globular cluster did not begin with the HST photometry. Spectroscopic studies spotted anomalies in the star's composition since a long time, and those anomalies presented with an alarming regularity. So light elements such as carbon, nitrogen, oxygen, sodium could vary a lot from star to star in the same cluster. And those variations are not in a random way. They vary in lockstep. So if carbon is low, then nitrogen is high. If oxygen is low, then sodium is high. And there are all combinations among those light elements. And this is just illustrated for 2808, one cluster, but this is not an exception. And the zoom plot shows the anticorrelation between oxygen and sodium, which is possibly the most studied among all the anticorrelation. What is important here is that this behavior, these large variations, are not seen among field stars. So there must be something different in globular cluster stars. Only part of the star in a globular cluster have the same light element abundance of field stars of similar metallicity. For all the others, we see the effect, some variation, and this is the effect of hydrogen burning at high temperature. For instance, in this case, oxygen is converted to nitrogen. So oxygen decreases and nitrogen increases, and sodium is produced by the neon sodium chain. Aluminum, for instance, is produced by the magnesium aluminum chain, and so on and so on. But this nuclear reaction may happen only at very high temperature, and those temperatures cannot be reached by the low mass stars that are alive now in a globular cluster. So these strange abundances must have been produced in more massive stars than the one we see today, of stars of a previous generation, which then polluted the material from which the stars that we see today formed. This interpretation has some problems. Some details are not clear at all, and this is normal. But the most probable thing is that globular cluster host stars that were not born at the same time and were not born with the same composition, at least as far as light elements are concerned. So this interpretation is based on a lot of observational evidence, and a good part of that evidence was collected by our group, and this has been made possible by FLAMES, a multi-object high-resolution spectrograph mounted at one of the ESO VLTs. The field of view of FLAMES, its wavelength coverage, the resolution, and the number of fibers available make it an ideal instrument to obtain and study stars in high resolution in the inner part of Milky Way globular clusters. So, along many years, we designed and conducted a survey of giant stars in 30 globular clusters to study the presence and the properties of the light elements anticorrelations. That was done to try and understand how the multiple populations were produced. And that means to understand how the clusters formed and how evolved in the first year of their evolution, let's say in the first 10 or 100 million years. So here you see part of our results, the sodium oxide anticorrelation for 25 globular clusters out of the whole sample. And our results are based on about 100 stars per cluster. So ours is a very large and very homogeneous set of giants in globular clusters, and it's second, I think, only to the apogee dataset. So thanks to flames and these large datasets, we were able to measure metallicity, stellar parameters, light elements abundances for many stars in a large sample of open clusters. And part of our, so we could see that the sodium-oxygen anticorrelation is visible in all globular clusters that have been studied. So we also propose that it could be a defining property of a globular cluster, separating this kind of cluster from other kind of clusters. And then we also studied not only the oxygen-sodium anticorrelation, but also the magnesium-aluminum anticorrelation. And we saw that it was visible and present, especially in the metal-poor and more massive globular clusters. And this has been later confirmed by Apogee and Gaia-ESO, two large surveys. So we also saw that the extension of the anticorrelation varied from cluster to cluster, and there was a correlation between the extension of those anomalies, variations, and the mass of the cluster. So mass is possibly the driver of the difference we see between clusters. And to prove that mass played a large, if not a dominant role in defining the multiple population, we try to observe not only the high mass globular cluster from which we started our survey, but to move also to low mass clusters. And then we also added very old and massive open clusters, Berkeley 39 and 6791, for which we did not find any indication of the same anomalies that, let's say, or not anomalies right now that we see in globular clusters. And indeed, if we look at a plot where we use age and mass of the cluster, we may see that the clusters that show multiple population, those indicated by red dots in this plot, are all massive, even if age may play a role in that. And of course, we are not alone following this trend, and there are other groups trying to understand what is the factor that determines the presence of multiple populations. So the culprits are mass, age, metallicity, the compactness of the cluster, or a combination of all of them. So this is something that really needs to be solved in some way. So this was what we did in the past, but let's move now to NGC 6388, which is the latest globular cluster that we studied. And on this cluster, I will go more in detail. So this is a very interesting cluster. It is a massive cluster, old, metal-rich, and is seen projected on the bulge. So it has always been considered a bulge cluster. And being projected towards the center of the cluster of our galaxy, there is a large contamination by field stars. So our first attempt with flames was not fully successful. And among all the stars that we observed, only about 30 turned out to be cluster members. And I recall that all those observations were done before Gaia was launched, so there was nothing to help us separating probable cluster members from failed stars in the interlopers. So our first attempt only obtained data for 30 member stars. But luckily, since this cluster is of interest to the astrophysical community, it has been observed also by other groups with flames, even if they didn't publish many results on that. So we were able to add their spectra to our sample if the spectra contain information on sodium and oxygen, or at least measure the radial velocity of the stars in those spectra, so we could select a highly probable members and propose new observation. So this strategy paid, and now we have 185 member stars instead of 30. That's something very positive. So one of the interesting things of this cluster is that it has been classified as a type 2 globular cluster. The classification is based on the combination of HST filters that produce the so-called chromosome map. And the chromosome map is a combination of different filters, space, ultraviolet, only obtained by HST or space telescopes, ultraviolet, blue, and near-infrared. And the combination of those filters is sensitive to variation in metallicity, helium, nitrogen, and so on and so on. So most of the globular clusters show a chromosome map where there are two clear, distinct zones, one occupied by the first population and the second by the second population of stars in the cluster. But there is a minority of clusters, the more massive ones, which show additional features in the color magnitude diagram and are called type 2. One of the possible characteristics of type 2 globular clusters is that they may show a spread in metallicity and a spread in neutron capture elements. And those variations are correlated between them. And indeed, a spread in metallicity has been found in some globular clusters. However, not in this case, at least not according to our measurements. So with our analysis, we did not find any spread in metallicity. Instead, we found a very tight distribution in metallicity, as shown by the red histogram here and by the plot up there. And this spread, the spread we find in our metallicity is completely explained by the measurement errors. So possibly no metallicity variation in this cluster are present. For NGC 6388, of course, we measured all the elements that go into the normal anticorrelation, all the light elements that were accessible in our spectra. So we obtained, beside iron, oxygen, sodium, magnesium, aluminum, silicon, calcium in all of the stars that we have. And here I show the improved sodium-oxygen anticorrelation, which moved from the 32 stars in here to the 185 in this cluster. And in this cluster, we can clearly separate the stars which are the same composition of field stars and which we attribute to the primordial component of the stars, and stars with modified oxygen and sodium, which we attribute to the second generation stars and of intermediate and extreme modification. So the fraction of first and second generation stars is about 30 to 70%, and which is normal when looking at sodium and oxygen. In this cluster, we were also able to observe not only red giant branch stars, as in the past surveys that we have done, but also stars on the asymptotic giant branch star, on the asymptotic giant branch, and on the red horizontal branch. And the anticorrelations are present among all kinds of sequences, but we see that the RGB stars show a more extended anticorrelation than AGB or red HB stars. So we could also measure neutron capture in all our stars, and those neutron capture elements like yttrium, barium, and others do not show generally spread. The only exception is zirconium, for which we found a significant correlation with sodium and with aluminum. So stars with lower zirconium tend to have lower sodium or lower aluminum. And this is something which is interesting because it has been found in some clusters, but not in others. So it is something that should be still studied more. And this, I think, it's a work that can be done better with the large surveys that will be done in the next future. And finally, on NGC 6388, I would say some words about the origin of the cluster. So it has been known for a long time that part of the globular clusters in our Milky Way did not form in situ in the main galaxy, but came with mergers. And nowadays, with the help of Gaia, it is possible to assign a given globular cluster to a given accretion event, even if there are a lot of uncertainties. And those may be solved by later Gaia data releases with more precise astrometry. However, I told you at the beginning that NGC 6388 is a bulge cluster, but there has been a suggestion based on the low abundance of a few iron peak elements, scandium, vanadium, and zinc, that the cluster could be could have been accreted to our galaxy. However, we think that this is not a correct interpretation, and based on the age metallicity relation and based on the chemical composition. So for the age metallicity relation, we may see here that the accreted and the in situ components of the globular cluster population populate two very different regions of the diagram. And NGC 6388 sits perfectly well on the in situ branch. To move it to the accreted branch would require to lower its age by more than 3 gigayear, which is something really implausible. And furthermore, a recent study by a completely independent group has confirmed that 6388 is a very old cluster. Then, if we move to the energy, which has been computed using Gaia and a Milky Way potential model, we can see, and we plot energy of the globular clusters versus their metallicity, we can see that different families of clusters coming from Sequoia or the Gaia, Sausage, Enceladus event, or the Helmi stream, or the main bulge or main disk components occupy different parts of this diagram. And again, NGC 6388 sits very well among the clusters belonging to the main bulge of our galaxy. And about the low metallicity with respect to field stars of the same metallicity, which could indicate an accretion from dwarf galaxy similar to the LMC, we did not confirm the low values of those three elements, scandium, vanadium, and zinc, found in the paper that proposed that this cluster has been accreted. But our study is based on at least 30, if not 185 stars, instead of the 4 stars that were used in that publication. So we trust our results, and we think that even the chemical evidence is for an in situ origin of this cluster. However, finding clusters with lower than average abundances of these elements at high metallicity works well in isolating stars born, for instance, in the Sagittarius dwarf galaxy. So the method seems to work, but NGC 6388 is a bulge cluster. And by the way, as a byproduct on this, since we were working that, we tried to use all the available information on age, metallicity, and the Gaia-based integral of motion to assign a more robust classification to some globular cluster of uncertain origin, combining energy with iron, age with metallicity, so this is a classical age-metallicity relation, and the angular momentum in the vertical direction with metallicity. So that way, looking at all the different plots, we could assign a more robust classification to a 10 or something globular cluster which had an uncertain origin. And of course, of this will be much more easier to apply once we get the next Gaia data releases. So, enough on that. It's time to move to the second topic of my talk, and to open clusters. So the family of open cluster is even more diverse than that of the globulars. And we have in that cluster, we put in that cluster objects that are just starting their formation and objects that are already a few bigger years old. So it's a mixed bag of objects. And open clusters are also much more numerous than globulars. Globulars in the Milky Way are about 150 to 200, and open clusters count in the 1,000. But exactly how many open clusters we have in the Milky Way is not clear yet. So I put here a few catalogs previous to Gaia, and then prepared using Gaia data release 2 or Gaia data release 3. So the number of open clusters increases because lots of new clusters have been discovered using Gaia astrometry and photometry, but also lots of clusters have been disqualified as clusters, again using Gaia data. So how many do we have? A few thousand. Not exactly sure how many, but the thing that we know is that open clusters are a disk population, are shown in those plots where I put the non-open clusters in the plane of the galaxy and in the plotted against 8 above the plane of our galaxy. So next question is, so I don't want to repeat now what I already said on the importance of stellar clusters for many astrophysical things, but I want to stress that we really need to use high-resolution spectroscopy of the largest number possible of open clusters and the largest number of stars in each cluster to answer to some of those issues named here. And then how many open clusters have been observed with high-resolution spectroscopy if we really need to use that to understand their properties. And the answer to this question is a little discouraging, because we have always said that only about 10% at most of all the known open clusters have their chemical composition derived by a high-resolution spectroscopy. But while the number of clusters observed by high-resolution spectroscopy increased, so did the number of discovered clusters. So we are say, always at about 10% level. So we don't know much about the whole population of all the clusters. So we will have to work on that. But in any case, I list here a few possible sources of abundances and chemical composition based on high-resolution sources. You can read that yourself. But in any case, it is always a small number of clusters compared to the whole population that we have in the Milky Way. I only wish now to stress one difference in approach between, say, apogee and Gaia-ISO. In the first case, the number of stars observed in each cluster is small, but they got many clusters. In the case of Gaia-ISO, instead, less clusters were studied, but at least 100 stars were observed in each of them, and up to 1,000 or a few thousand stars. And they were chosen following the evolutionary sequences, so we have stars in each of evolutionary phases in every cluster. And we got objects from the star-forming regions to very old open clusters. So there is a difference in approach that is important. And one thing I need to add is that most of the surveys have been done in the optical regime, and apogee is the only exception right now. So our idea was to try to combine all this, optical and infrared, and adding a very high resolution to the game. And this is possible because there is an observational facility called JARPS, mounted at the Telescopio Nazionale Galileo on Canary Island, which is a 3.5-meter telescope. And JARPS is the combination of two spectrographs, two high-resolution spectrographs. One is ARPS North, which works in the optical at a resolution of 115,000, and the other one is JANO, working in the near infrared from the Y to the K band, and it also works at high resolution, 50,000. And what they do is that they work at the same time. And there are not many such instruments around the world. One for instance, is NIRPS at the 3.6-meter telescope at ISO, which is a combination of ARPS and a near-infrared spectrograph, but there is no K-band in that. So we use JARPS in the framework of a large program called SPA, Stellar Population Astrophysics, at the TNG. About one-third of the time of the large program was dedicated to open clusters. And our strategy on that was dual. Either we aimed to observe a large number of stars, but in that case, limiting our observation on a few giants in each of them, or we tried to observe as many stars as possible in a limited number of close-by clusters. So the two approaches, of course, answer different goals and different needs. In one case, we get metallicity and detailed abundances for many clusters, and that this is useful if you want to get precise ages, because to get precise ages, you need a precise metallicity. And we can get a chemical map of the distribution of metallicity and abundances in the disk. In the second case, with observing many stars in the same cluster in different evolutionary phases, when we can test stellar models, because we can test the effects of mixing and diffusion, we obtain information on all the nucleosynthetic chains, and we can get information to chemical evolution modelers, and then we can have information on the activity, on the rotation, on the binarity fraction, etc. And then, since we have access also to the infrared at very high resolution, we can get also elements like helium, fluorine, and phosphorus, which are not observed normally, and they are not observed at all by the large surveys. So those plots show the distribution in age, distance, and number of stars observed by SPA open cluster. And we observed 50 clusters with as low as 1 star and as high as about 30 stars in the same cluster. And since the TNG is a 4-meter class telescope, we are working with very high resolution spectroscopy, we have to limit to distances to about 2 kpc from the sun. So, just to give you a flavor of what SPA open cluster is producing, here is an example of strategy number 1. Few stars, many clusters. And in this plot, you see some results based for 16 clusters that had never been observed before, for metallicity and for alpha and light elements. There is no need to dwell on that. I only wish to stress something visible in the upper plots. In this, we compare our metallicity and the metallicity derived by other sources with models of chemical evolution of the disk. And while generally for older clusters, the chemical evolution models reproduce pretty well the observed distribution, here there is a problem. The low metallicity of young clusters in the near us. So those clusters lie close to the sun, but have apparently a metallicity lower than that of the sun. This is not something that only we have found. It is a known problem. It has been found by others, and this is due to the fact that those young stars are very active atmospheres, and those active atmospheres with magnetic fields, etc., are very difficult to measure well. So be cautious when you see low abundances for very young stars, because it may be something related to the analysis and not really the true metallicity. And this instead is an example of using strategy number 2. So the cluster stock 2 is a very close by cluster. It is young, but not too young. And we observe stars both on the main sequence of the cluster and in the red giant region of the cluster. So for each of those stars, we could measure individual radial velocity, rotational velocity, reddening, metallicities, abundances, etc. And we could find some binaries among our stars, etc. And besides the measure of the metallicity of this cluster, which is, by the way, the same for stars on the main sequence and giants, and this is, of course, a good thing, but it's not guaranteed that analyzing stars, dwarfs and giants, you obtain exactly the same results because of problems in the analysis method. We see that there is a huge differential reddening in this cluster, and this differential reddening explains the width and the extent of the main sequence turnoff in this class, which is an extended main sequence turnoff. And the differential reddening explanation works, in our case, better than a variation in rotational velocities. And with the stars on the red side of the diagram rotating at velocities different from those on the blue side of the diagram. But since these effects on different rotational velocities has been found in other clusters, it would be interesting to study more clusters and understand why in some cases this is present and this is not. So moving away from results based mostly on HARPS spectra, I said that we used JANO. JANO works in the near infrared, and that permitted us to derive the abundances, for instance, of fluorine. Fluorine has no lines in the optical, so it has not been measured in a lot of stars and in a lot of clusters. And for instance, as I already told you, none of the large surveys cover fluorine. And why are we interested in fluorine? The source of fluorine is not well known. So it has been hypothesized that it is produced by AGB stars, by core collapse supernovae, by rapidly rotating INAF stars, by novae, etc. So we can provide modelers with precise fluorine abundances for objects like open clusters, for which we may measure the age pretty well, and which are ages from a few million years up to a few giga-year. So we can follow the evolution of fluorine enrichment in the disk of our galaxy using open clusters and providing constraint models. Our first results have been the paper has just been accepted on ANA, and it is a pilot project on 7 open clusters observed in the SPA Open Cluster Survey. And we see that we require a mix of sources for the production of fluorine. AGB stars are required, but also massive stars with different rotation levels. So we have new observations coming, so we can do that for a larger sample and give better constraints to models. And finally, one last slide on SPA open clusters, again showing the benefit of joining optical and near infrared. In this case, trying to measure helium. Helium is very important for stellar structure, but it is an element very difficult to measure, especially in giants and especially in the optical. So we are trying to see if we can measure helium from a near infrared line at 10,830 angstrom. And I show here in those plot this line in 2 giants of the cluster stock 2. So you see that this line has very different strength in the 2 giants, even if those stars should have the same helium because they belong to the same cluster, and the stars are very similar, so they have very similar atmospheric parameters. So there is something here. This is the problem is that this star is a chromospheric line, is not an atmospheric line. So that means that translating the equivalent width to an actual abundance of helium is not straightforward at all. And the variation we see between stars that should have the same helium is due to the different level of activity in the 2 stars. And one important thing is that we can measure the level of activity of our stars because we have the spectra taken with arcs north exactly at the same time as the JANO spectra. So we may see from the region of the calcium 2 H and K lines that the activity in this star is much less than the activity in that other stars. So we can try to correlate the level of activity to the width, to the strength of the helium line, and we hope that we will be able to get actual measurements of helium in the future, not only in this cluster, which again is a pilot project, but in all the clusters in our sample. So in the last few minutes, I will briefly mention two new surveys, large surveys. So future surveys, in that case, WIV and FORMOST. And while FLAMES is a wonderful instrument and it's ideal for the central part of the stellar cluster in our galaxy, we really need to move farther than that, because we know that part of the cluster stars do not reside in the center, but in the outskirts, in extended halo, in tidal tails, and so on and so on. So the new generation of wide-field large multiplexing spectrographs will permit to cover the entire cluster from the center to the outskirts and even beyond that. And in particular, two surveys have just started or are going to start soon, and those surveys take their names from the instruments that they use. So WIV is in the northern hemisphere. The WIV instrument is mounted on the 4-meter William Herschel telescope, while FORMOST is in the southern hemisphere, and the FORMOST spectrograph is mounted at the 4-meter VISTA telescope. WIV is a private service and is conducted by the consortium who built the instruments. FORMOST instead is a public ESO survey. Both surveys will run for 5 years, at least. And there are many similarities between the two surveys. For instance, the large field of view both have a diameter of about 2 degrees, a large number of fibers, about 1,000 for WIV and 2,400 for FORMOST. The resolution, 5,000 in low resolution mode and 20,000 in high resolution mode, which is not really very high resolution, but it's not bad at all. So, and so on and so on. And WIV has already started the operations. There have been commissioning and science verification and some observation in the IFU mode have already started. FORMOST is being assembled, and it should start sometimes in 2025. Of course, as usual, those dates can be a little shaky. So, as part of the WIV Galactic Archaeology survey, because WIV is organized in different surveys from the extragalactic quasar and Milky Way surveys. As part of the Galactic Archaeology survey, we are observing open clusters. So we plan to observe from 200 to 300 open clusters, and this is also because we can make good use of the large field of view of WIV, because often more than one cluster fall in the same field of view. So the Galactic Archaeology Open Cluster Survey will observe clusters of all age, from star formation region to very old cluster, and we will get as many stars in each cluster. Remember, we have about 1,000 fibers at in our hand, so we can try to get stars all along the evolutionary sequences. There is one small problem. Not many globular clusters will be observed about 10 of them only because of several problems that are too long to tell, but there will be some. On the other side, the survey stellar clusters in foremost in the south, we has a different strategy. We will target all accessible clusters from the south, from star-forming region to globular clusters. So there will be a lot of interesting stuff here. So for stellar clusters, WEAV and foremost are highly complementary. In one case, less clusters will be observed, but with a higher completeness, and it will be possible to study internal kinematics, to follow the cluster from the center to the tails, follow the effect of stellar evolution of stars in different phases, etc. In the other case, many more clusters will be observed, but a smaller completeness. But since all the observation in foremost are taken at the same time, we will be able to use the observation taken in different parts of the disk and the halo to follow and observe tails all over the sky. And again, as a complementarity, foremost will have a very good coverage of globular clusters, so it will be possible to obtain information on chemistry and internal kinematics also for them. And finally, a very sketchy, very short summary. And the important thing that I want to note here is that all the surveys mentioned have public catalogs, and the spectra are available for anyone to use and to analyze. So this may encourage us to find new projects, not only the ones that were originally in the survey's main goal, and to provide new ideas. So archives, I love archives. Archives are really a treasure trove. So with that, I thank you very much for your attention today, and I leave you with an announcement for this conference, hoping that some of you plan to come to Bologna soon.
Thank you. Very nice seminar. Now let's open for questions, first from the audience. And if we have people in Zoom, can you please raise your virtual hands? Audience? I have one then, while you think. So very nice review. Sometimes it's very hard as students to really search the literature of all these multiple population phenomena and all the clusters. And you gave a very nice overview. So thank you. I was wondering, something else that you didn't touch upon is, so we haven't been able to solve the multiple stellar population problem or issue, whatever. But there are some claims from Z11 galaxies, like the GNZ11, or that is actually a redshift 10.6, that they have, there's claims that there's nitrogen over oxygen abundances that are very similar to globular clusters. So I was wondering, what's your opinion on that? And if you think we might learn more we might solve this multiple stellar population phenomena by looking at high redshift galaxies forming globular clusters, or we should be looking locally?
We should do both. It is a very interesting way to solve problems, and this has been tried before, even before the James Webb Telescope, to try and see if we could find, well, if not globular cluster as we see today, the structures that would become globular cluster later on. And yes, I think it is a very good way of looking at the problem, trying to find the precursors at very high redshift. And if it is possible to measure nitrogen and over oxygen abundance, and if this is found enhanced, that means that at that moment, that structure is the precursor of a globular cluster. And the masses are okay. It is difficult because even with the James Webb, you need, I think, a high magnification with lenses to obtain good spectra and good abundances for that. But I think it's a good thing. But we shouldn't do both. Try to observe nearby clusters, but well, okay. It's not that we have already done all of them, but lots of them. But try to also find clusters which are just forming. So to confirm or disprove that we need to have an age difference of a few tens, a few 100 million years between stars in the same cluster to explain the abundance that we see.
Questions, Basile?
Thanks for the nice talk. At some point you showed, I think, on the TNG results that young clusters close to the solar circle region, they are under, yes, that's the plot. They are under abundant as compared to chemical evolution models. Now, and you blame that on chromospheric activity, if I remember correctly.
It is not chromospheric, it is activity. Those stars have strong magnetic fields, spots, etc. So it is difficult to analyze spectra of those stars because, yeah, it's not a static atmosphere.
Right.
And it's not, yeah.
Okay, my question is, there are, I mean, I wonder if there could also be an explanation based on dynamics. There are some claims that the co-rotation radius of the galaxy could be close to the solar circle, and at co-rotation, perhaps chemical enrichment could be at a slower pace because of a less violent interstellar medium. Could that perhaps also help explain these underabundances?
It could help, but I don't think it is the preferred explanation because if we can measure young stars, even not in the close vicinity of the star, we see the same effect. So I think the preferred explanation is that one. But we will soon see because lots of those stars will be targeted by WEAV and Foremost. And in Foremost, there are groups of people who are trying to prepare for the analysis of those stars. So K and M type stars are difficult to analyze on the main sequence for those objects. So, but of course, anything can help. So if there is a lower enrichment, that's okay. But I don't think this is an explanation also because those models that you see here take into account radial migration, for instance. So.
Okay, thank you.
Okay, more questions from the audience or from Zoom? Questions from the students? No?
Another thing for the multiple population is to increase the synergy between photometry and spectroscopy. So we can go all the way with high resolution spectroscopy, but it will be only on part of the star. With photometry, and especially with narrowband filters, then you can observe the whole cluster population. And if you find narrowband filters sensitive to variations in abundances, then that will help.
We have one question.
Yeah, sure.
Sorry. We have one question from YouTube that is, thank you for the talk. I would like to ask, how are ages determined in most of the clusters, especially in globular clusters, main sequence turn-offs and white dwarfs?
Okay, the ages are generally determined using comparison with isochrones. Stellar tracks, if you prefer to compare synthetic color magnitude diagrams to observe diagrams, but the age is always determined by comparison with stellar evolutionary models. So isochrones, for instance, and you need the position of the turnoff, but in the case of globular clusters, also the position of the horizontal branch helps a lot. So there have been many works in the past trying to measure ages, but the most, the most accurate ones are based on stellar models. For white dwarfs, it is possible to determine age from the white dwarfs, but the problem is that globular clusters are usually quite far, so it is possible to observe the whole population of white dwarfs only for the one that are close to us. But it has been done also, comparing cooling sequences to the population of white dwarfs in the same cluster. So there are many methods, but they are always based on models.
Thank you. More questions? If not, let's thank Angela again.
Thank you very much.
Thank you. Bye-bye.
Bye.